Good morning, class. We are in the middle of the thermal chapter. We'll be talking about the fundamentals of heat transfer. So a little bit of physics, thermodynamics, math, and how to do thermal analysis. So let's start with the fundamentals of heat transfer. So I want to get you all started with some basic knowledge of the different mechanisms that govern the physics throughout the system. So there are 3 different heat transfer mechanisms, and they're all shown in this very common cartoon of how heat transfer is demonstrated. So on Earth, we have this stove that is radiating heat. So you can feel that even if you're not touching it, it's just transmitting. If you have a boiling pot of water, you put the pan on the stove to conduct heat through the bottom, and then the water will circulate with convective forces. You can also feel conduction on the handle when you're touching the pot handle. So let's dig into a little bit more of each of them. So conduction. Let's see, conduction is, remember when we were talking about the kinetic particle theory, how temperature can be measured in thermal energy due to the vibration, the energy of the microscopic particles that this bulk material is made out of. So you can take that concept, and if you have 2 bulk materials of differing temperature, then you're going to have, say, this higher temperature material in contact with a lower temperature material, and the particles will transfer energy at the boundary. When that energy is transferred through a boundary, it's called heat conduction. And so you'll see this symbol here, Q, which stands for the amount of heat or energy that is being transferred across that boundary. You can see this interaction here, so we've got a bulk material at T2, and we have this conducting solid, and we have a cold environment at temperature T1. These are the different variables that you would need to know about to estimate the temperature gradient across this conducting solid. The governing equation is up here. The amount of heat transfer Q is proportional to the thermal conductivity K, the area A, and the thermal gradient dt over dx, where dx is that difference in length, and dt is that difference in temperature. You'll notice here there are many variables at play. So K, the thermal conductivity, relies on the material that the heat is flowing through. Different materials have different conductivities. It depends on the surface area of the materials that are touching. So that cross-sectional area where heat is actually flowing through. And it depends on the difference in temperature and the length, as we talked about. What else do I want to say? Okay, let's keep going. Oh, okay. One more thing. Remember the requirement to ensure that components are properly fabricated and integrated? We see this variable A for area. This is the reason why we want to ensure sufficient amount of surface area is touching when creating a connection to enable thermal control through conduction. This is important if you're relying on conduction. You want to make sure that the surface areas are really well flush to each other. So let's look at some thermal conductivity of common materials on spacecraft. So aluminium, as the British would say, or aluminum in America, the thermal conductivity is about 237. It's typically used as the structural frame of spacecraft. So this could be important, say, if you had electronic boxes that were dissipating heat, and they were mounted to the frame of the structure, you can use this conduction to transfer the heat dissipated from the electronics to the structural frame. Copper has a higher thermal conductivity, so you'll see this material being used a lot for things that need to be electrically conductive and also thermally conductive. It's typically used for electrical interfaces and grounding planes, and on Friday you'll see that it's used a lot for heat shunts and strips. Silica aerogel has a very low thermal conductivity, where it's more like an insulator. So its spacecraft use is for insulation. Water, which can be used to thermally regulate or as propellant, has a relatively low thermal conductivity. And polycarbonate, which is what we make printed circuit boards out of, so a lot of electronic boards, also has a relatively low thermal conductivity. So you can manipulate the placement of these materials to toggle or throttle the amount of conduction that you want to see between different components of different temperatures. You can also think of thermal conductivity as electrical resistance, in the way that both properties represent the ease at which energy transfers through a material. I'm going to go back. Yeah, so K you can think of as resistance, and A you can think of if you have a very large wire, then you can transfer a lot more current through it. The same concepts can be thought of with like pipes of water. The larger the area, the more you can shove through. Okay, this equation here is a different form of thermal transfer. It is it's a differential equation that is more commonly used for finite element analysis. So I just want to get into it. So the amount of heat that is transferred is related to the thermal conductivity and the temperature difference, but also the density of the material, the specific heat of the material, and the temperature over time. So this equation is a little bit more rigorous in that you can define time as well, not just a function like instantaneously this is the amount of heat that is transferred. This equation is more about the time solution. I do not know the approximate K of ammonia, but I can look that up later. Tomorrow I'll be talking about ammonia, so that'll be a good time. Why don't we look it up now? Milliwatts per millikelvin. Let's say at 300, which is room temperature, it's about 1 bar, 65. Yeah, so 65 is like 2 orders of magnitude more than water. Okay, moving on. I guess that's a good transition to convection, which is the transfer of thermal energy through fluids. It can be, a fluid can be a gas or a liquid, and we're not really interested in it too much because for small spacecraft, it doesn't scale well. So I just wanted to show you pretty pictures about how it works conceptually. So we have a cool medium and we have a warm medium, and due to gravity, there's this circulation that happens. Cooler gases are less, more dense than warmer gases, so there's this convection that's happening. Here is a simulation of thermal convection. This is an illustration taken from a model of convection in Earth's mantle. So just know that this exists. And for our smaller spacecraft, we don't use it very much, but it's good to know if you want to work on larger spacecraft. All right, radiation. So we are going to talk about radiation quite a bit today because it is the pretty much dominant force for heat transfer. Radiation is the emission of electromagnetic waves, and it does not need a medium for transport, so radiation works in a vacuum. The equation that governs radiative heat transfer is given up here, where the rate of heat transfer by emitted radiation is determined by the Stefan-Boltzmann law of radiation. That's what this equation is called. And accordingly, the Stefan-Boltzmann constant is this sigma. It's about 5.6 times 10 to the negative 8 joule per second, meter squared, Kelvin to the fourth. E, or epsilon, is emissivity. A is your area. And then the temperature is heat transfer scales with temperature to the fourth, where T is the temperature of your body and T, environment, is of the environment. And you can assume that when you're in space, the black body radiation of outer space, deep space, is 3 Kelvin. Now the units here are, you just gotta make sure your units are consistent. If we were to do SI, then A would be meter squared and T would be in Kelvin. Okay. So let's look at these two bodies. Here is a black body where your absorptivity and your emissivity, which are two separate material properties, are approximately 1. So a black body absorbs all the energy and it also emits all the energy. They call it a perfect black body. A white body has an alpha, or absorptivity, and an epsilon, emissivity, of about 0. Now in reality, we don't have perfect black bodies or perfect white bodies, but we do make certain assumptions, and where possible, we measure these properties when doing more refined simulations. Okay, let's break it down. So emissivity and absorptivity, they are different. Emissivity is the transmission, so you're emitting, whereas absorptivity is the reception, you're receiving. Emissivity is a material property that indicates the radiation of heat from a body. Emissivity ranges from 0, a white body that reflects radiation, to 1, a black body that absorbs all heat. Values between 0 and 1 signify a gray body that partially reflects and absorbs at some ratio. Emissivity and absorptivity are both dimensionless values. They are ratios. Absorptivity of the surface of a material is its effectiveness in absorbing radiant energy. I want you all to note that for a given wavelength, absorptivity or emissivity across wavelengths can differ. So you can have a different epsilon value in the visible wavelength range and a different one in the infrared wavelength range. Typically, we assume that emissivity and absorptivity are the same, but as you'll see in this table down here, that's not always the case. You can have something that is more emissive than it is absorptive, and vice versa. So let's look up here at the emissivity of common materials. Quick note, the picture on the right shows that materials with higher emissivity appear to be hotter. In this thermal image, the ceramic cylinder appears to be colder than its cubic container, while in fact they are the same temperature. I believe that this picture is captured by measuring infrared spectra. So that's one way to measure, I guess, emissivity. All right, so emissivity of different materials. We've got highly polished aluminum. It's about 0.039, so it's highly polished. I think that's the key defining feature of this material. And so when you highly polish something, it's closer to a white body. Whereas I think someone had pointed out that anodization affects material differently. Absolutely. In this case, anodized aluminum has a higher emissivity, so it's closer to a black body. But both are used for structures. So in the process of creating your satellite, if it turns out that you're running hot or running cold, you can treat your aluminum differently to get these different emissivities to then modify your, say, equilibrium temperature of the spacecraft. Okay, amorphous silicon, which is a common solar cell material, and since solar cells are on the outside of a spacecraft surface, you care about how they emit. So they range between 0.45 to 0.8, so it's closer to a black body. Copper, closer to a white body. Silica aerogel is an insulator, again. It has higher emissivity values. Water, very high emissivity. And also the case with polycarbonate for PCBs. Okay. The ratio that we want to control for is emissivity to absorptivity. Or in this case, this table is reporting absorption over emission. So aluminum has different absorptivity than it does in any emissivity value. Its ratio is 3, so it's going to absorb more than it is going to emit. The aluminum, in this case, is going to make the body warmer because it's going to absorb more than it's going to radiate away. White paint has the opposite effect. It emits a lot more than it absorbs. So that's why a lot of spacecraft components that run hot and want to stay cool use white paint just to coat the surface. Black paint, it seems to equal out just about. And then silver Teflon, it's even better at keeping things cool. So yeah, pay attention to these different materials because they can really affect in the long run, over time, how thermal energy is retained or just radiated away. Okay, so I just said this, but on the other slide, as to review, the absorptivity to emissivity ratio is really important when thinking about the equilibrium temperature of your spacecraft. So silver Teflon minimizes solar absorption, maxes emissions. It's used a lot for telescope mirrors. You can see the Hubble is quite silver. The use of black paint is to maximize energy transfer, both for absorption and emission. So here we'll see an ultra black Vantablack surface coating material. The use of metals minimizes both absorption and emission, so that could be good for instrument sun shields. And you can combine these surfaces to get almost any ratio you want. You may even paint your spacecraft different colors based off of the amount of heat that is centralized or localized in that one area. So yeah, it can get pretty creative. Okie dokie. So let's talk about the different type of radiative interactions in space. So hopefully you'll get comfortable with this image where the thermal balance of a spacecraft is seen by taking the net sum of these different interactions. We have the spacecraft radiating heat into deep space. We have the spacecraft absorbing solar radiation directly from the sun and indirectly through the reflection onto a planet called Albedo, and also absorbing Earth radiation coming from the heat of Earth. So let's go into each of these different equations, and then at the end of this activity, we'll actually get real numbers for our CubeSat and see what our equilibrium temperature is going to be. So, thermal radiation to space. This is the amount of energy that is flowing out of your spacecraft. Recall the Stefan-Boltzmann equation, where the amount of heat that's transferred out of your spacecraft is going to be the emissivity at your wavelength times the constant times your absolute temperature to the fourth and the amount of area that is radiating outward. So let's look at this picture over here. So this picture is a demonstration of Wien's law. The reason why we use Wien's law is because radiation is emitted at all wavelengths. So what lambda, or what wavelength, do you actually choose that dominates this effect? We use Wien's law to determine the wavelength that is most dominant. Here, you'll see that the spectral energy density for this green curve is the most dominant, and that occurs at about 500 nanometers. So that is the wavelength that we would define the emissivity at. Okay, for our CubeSat, let's just say that we have a surface emissivity of about 0.8. This is going to be the case for, well, we'll see. Let's just say that the emissivity is 0.8. Then we have the Stefan-Boltzmann constant. Let's say that the spacecraft is at 330 Kelvin. So that's about room temperature plus 30. It's pretty warm. 30 plus 30 is about 60 Celsius. And then we have the surface area, which is about 0.01 meters squared. The amount of effective heat that is radiating out of the spacecraft is about 5 watts. When it comes to the heat that is being absorbed by the spacecraft, solar is one of them. So here we have the spectral irradiance of the sun at different wavelengths. We're going to take the visible as the dominant effect. So IS is the solar irradiance around the Earth. It'll be the value, peak value there. Alpha is the absorptivity. And because we're looking at the visible wavelength range, we'll take alpha, or the absorptivity, at the visible wavelength. And then A is going to be the area that is perpendicular to the sun vector. It's the surface area of the face or faces that the spacecraft is indirect viewing of the sun. So in this case, the spectral irradiance is about 1360 watts per meter squared in low Earth orbit. Our absorptivity is about 0.4. And the surface area that we have facing the sun is about 0.01. In this case, the amount of heat absorbed by the sun is 5.44. All right, so now we need to think about, if we're in low Earth orbit, the albedo is going to be also radiating some heat to the spacecraft that will absorb. The amount of heat from albedo is related, again, to the spectral irradiance of the sun and our absorptivity in the visible wavelength range. But now we need to think about R, which is an albedo coefficient. It's pretty much some scaling to reduce, it's like the amount of, the percentage of diminished power that the sun has because it reflects off the earth instead of being a direct like line of view. In most cases, R is going to be between 0.2 to 0.6. And then A of the earth is the amount of area of the spacecraft that is facing the earth. So we'll just assume that it's just a single face of the spacecraft. So again, you'll recognize this, the solar radiance, 1360 watts per meter squared, our absorptivity, 0.4. And then just take the average of R, we're going to use 0.4. Face of the spacecraft is 0.01. So our heat from albedo is going to be 2 watts-ish. And then finally, the amount of Earth's thermal radiation just coming from, Earth being a warm body is going to be a function of the emissivity of the Earth in infrared. F is some geometric factor called the view factor. Excuse me. Alpha is the absorptivity of the spacecraft in the infrared range. Sigma is the constant. T is going to be the temperature of the Earth. And A is going to be the amount of area of the spacecraft facing the Earth. So if we take those values where, in this case, I used an epsilon infrared of 1. Hopefully that's consistent. Anyway, this is a thought process. Just make sure that your emissivities are consistent between wavelengths. So epsilon of infrared is the same, but your epsilon of visible, for example, can be different. Anyway, F, view factor, 0.28, usually calculated through some long spreadsheet or calculator. Our alpha in infrared is 0.4, Stefan-Boltzmann constant. The temperature of the Earth is 255 Kelvin on average. That's the temperature of what we assume the Earth would be if it were a black body. And then the area facing the Earth is about 0.01 meters squared. So you'll see in this case, Earth's inherent thermal radiation is about 0.27 watts for our spacecraft. And then I didn't talk about this in the radiation diagram, but your spacecraft is going to be internally dissipating heat due to the electronics not being totally efficient. So we have all of our different boards here that are using a certain amount of power. And then what I've assumed is that they're not totally efficient. If they were efficient, then all of these numbers would be 1. But instead, I'm going to say they're maybe 95% efficient in using the power to do useful calculations. But 5% of that power is going to be converted into thermal energy. So in that case, if 5% is being converted into heat, then this is the amount of heat that each component gives off for a total of 0.73 watts if everything were on at the same time. So then our radiation balance would be, so remember this, your Q in is going to be the amount of Q out, where Q out is a function of temperature. Now, what is Q in? It's all of the sun, the albedo of the Earth, and your internally dissipated electronics, where your Q sun is this equation, so you recognize these equations. So one equation and one unknown. This is the one equation, and our unknown is going to be the final temperature, the equilibrium temperature of our spacecraft in the end, where we're assuming that the spacecraft is just like a single node. It's the simplest assumption that it's this point in space and everything is just homogeneously clumped together. So the solution is the mean temperature of the entire spacecraft. But this is an assumption, right? In reality, the spacecraft is going to have a thermal distribution of hotter spots and colder spots. But for the sake of this equilibrium temperature at a point, this is the equation we use to figure out what that equilibrium T is. So let's walk through it. Our Q sun, remember, is 5.44, Q albedo, about 2 watts, Q earth, 0.27, Q internal, 0.73. That takes our total internal, the amount of heat coming into the spacecraft, 8.63 watts. Now, if we assume our spacecraft is 330 Kelvin, the amount of heat that the spacecraft is radiating out is 5.38 watts. Now, this means if our spacecraft were at 330 Kelvin, it would be taking in about 3 watts more power in heat. So it would rise in temperature. The spacecraft would settle into equilibrium when the amount of heat going out of the spacecraft system is equivalent to the amount of heat coming in. So the temperature in which that is the case is 371 Kelvin. The spacecraft at that point, at that temperature, would be radiating out the same amount of heat, 8.6 watts, as it is taking in. Now 371 is 100 C about, and that is a hot spacecraft. I think that would be quite unpleasant for the spacecraft. We're going to toggle alpha to be, instead of 0.4, 0.2. If we were to toggle alpha, then the amount of heat coming into the spacecraft, so you paint the spacecraft with a better white paint that's more reflective, less absorptive, then in that case, you could scale all of these values down. Q earth, Q albedo, and Q sun are about all halved, and the amount of heat going into your spacecraft is about 4.7. And the equilibrium temperature, where Q in is equal to Q out, is about 319 Kelvin. So that's getting to a more comfy range for the spacecraft. Hopefully that was a good demonstration of, all of the radiative interactions that are going on in space, and how to figure out equilibrium temperature for just like a very back of the envelope case.